Hello everyone, this is Sharad. This presentation is a part of Compi 255. Today we'll be looking at wildfire detection and spread modeling. We'll be seeing how we can detect wildfires and predict the spread to limit damage. Uh, Wildfires are natural, they occur naturally. They burn down a large amount of vegetation. In the US last year alone, 9 million acres of forest was burned, and other effects are air pollution, land degradation, and it also causes a humanitarian crisis where people are displaced, wildlife is displaced, killed. So it is really important that we detect these fires early and do everything in our capacity to limit the damage. We are trying to build a machine learning model which can detect these wildfires early, so we can notify the ground staff, and we can initiate necessary action as soon as possible. For this, we'll be using satellite images uh, and also uh, with advanced technologies like computer vision and neural networks, deep learning. We are making an effort to detect these wildfires as soon as possible. And we'll also be using mathematical models and neural networks to predict the spread pattern of the fire. So once it starts, we can predict where the fire propagates and take necessary actions like evacuation or taking fire prevention measures. Uh, we'll just look at what is computer vision and deep learning very briefly. So the term computer vision is actually self-explanatory. So it is the ability of the computer to read an image and gain insights based on that image. So the advantage of using this method is that we do not need to do any heavy pre-processing um, before we feed these images into our model to train. And we do not have to convert these images into numeric data. The neural network will be able to read these images in the same format. And deep learning is a classification of artificial intelligence and machine learning. It can learn from the data by performing transformations. These transformations occur in phases, and they work by performing these transformation in layers. So the whole idea of deep learning is to implement a learning mechanism which is very similar to the human brain. So basically, any task that a brain performs regarding computer vision is divided into classification, prediction, or segmentation. So we are either classifying objects, distinguishing objects, or predict what is going to happen to those objects. And we'll be able to use this in a deep learning algorithm, just like how the brain works. Uh, Coming to our data, so to uh, to train these models, we'll be using aerial images or satellite images of the land below. So we have multiple sources of data available. Some of them are like the research P satellite. We also have aerial images from space agencies. We also have data images available from private organization, and I've just put in a link. This is actually a publicly available data set. We just have to go in and sign an agreement telling that we'll be using it for academic purposes, and we'll be able to get these images. Uh, but because we are using data from various sources, I mean, obviously there is going to be some sort of variation in them. They can change in size, color, and some of them could actually be really noisy. So we need to get all of this into a standard format, work with how to reduce noise, and uh, and then we can feed this data into our training model. Uh, but again, we do not need to pre-process this data heavily because we do not need to manipulate the data in terms of uh, its sense, basically. So to reduce the noise, we can align these images, stack them, So images with low resolution are enhanced, and these images may be in various other color schemes, like it could be natural light, it could be infrared. Uh, so what we actually do is we normalize the data within each pixel. So we'll have the data in the range of 0 to 255. So we can represent each pixel using a number in this range, and the images will still make perfect sense. We are not changing the context of the image. One other thing that we need to do is these images are in fragments, because they're taken in bits and pieces. We just need to stitch them together. We overlap them at the edges. There is this phenomenon which happens when doing this. If we are not overlapping those images, the boundaries of the individual pieces may actually give us false information. So we overlap them and correct them basically. And then once we have all the images, we'll be sampling those images by using data windowing. So each window will be 256 into 256 pixels, and we do it in steps of 128. So which means every sample, we move the sampling window by 128 pixels. Uh, uh, and because these images are hard to get, uh, I mean, the availability is quite less. So what we do is we augment the data, we rotate each image, we mirror each image, and we scale this image so it shifts. And the result of this is that we have 8 times the data set. So if we have one picture, after all these transformations, we'll have 8 pictures. So that is the advantage of data augmentation, and that is all the pre-processing we'll be doing. The next step will be to train a model. So first of all, we'll have to identify our target variable. So the target variable or the result of uh, of the model will actually be a binary masked image. So we'll convert all our training data set into binary masked images before feeding into a neural network. And for training, we'll be using a neural network called as UNet. UNet is a very popular convolutional neural network. The output of this neural network is actually a binary mask providing the information if the image actually contains a fire or not. So uh, these training actions are actually computationally very heavy. Uh, the, the research paper this presentation is based on, the researchers have used an NVIDIA DGX1 supercomputer to do the training, and uh, the architecture of UNet is actually shaped in a U, and hence the name UNet. It has 3 phases. One is encoding. It is also called as compression, bottleneck, and decoding or expansion. And it uses a combination of convolutions and max pooling transformations to train a model. The advantage of UNet is that it combines the data from encoding and decoding phases, and ultimately gives us an image segmentation map. So the basic operation being performed here is segmentation. We are segmenting if an image contains a wildfire or not. So uh, the output is an image segmentation map, which contains information if the uh, you know uh, which is essentially transformed into a binary masked image, and it can be then labeled as fire or not fire. This is the architecture of the UNet model. On the left hand side, we are inputting the image. This is the size of the image, and during each transformation in the encoding phase, we are decreasing the size of the image and transferring some data back to the decoding phase. This is the bottleneck phase, and on the right hand side, we have a decoding phase. These are the data channels between the two phases, and ultimately we have an output segmentation map. There is this nice video which I have linked in the references. Uh, it is by a YouTube channel, and they've done a pretty good job of explaining the neural network. So I would suggest everybody can refer that if they need more information. This is the input that we are feeding into the model. So this is our image, this is our binary mask, um, and this is the output that we are getting. So this is the image, this is the input, uh, or true mask, and this is what is the output of a neural network. We can call it as a predicted mask, and that gives us information if a part of the forest actually has wildfire or not, and based on that we can alert the ground crew and uh, initiate necessary actions. So we'll move on to the next part of this presentation, which is spread modeling. So once we have detected the wildfire, it will obviously take some time to extinguish it. Uh, but by the time, it could be too late, or the fire can be spreading so fast that the surrounding communities, the wildlife, the forest could be in danger. So we'll have to take action where we can evacuate people, rescue animals, or take fire prevention measures in the surrounding areas. And that is where spread modeling comes in. So spread modeling basically helps us understand how the fire propagates. And this is based on a few factors. So one is topography, vegetation density, heat conduction, and wind. And these are the factors which affect how a fire spreads. Our aim is to build a model which will take into consideration all of these factors and give us a probability of where the fire will be spreading next. We are using satellite images once again to get the information regarding topography and vegetation. We need to make images more contrasting, more enhanced. So we normalize it using this formula. So it is I equals alpha, IRGB, beta, IHSI, and gamma IF, where A, alpha, beta, and gamma are mixing coefficients. So we, based on the image, we take into consideration different proportions of each of these components. And alpha, beta, and gamma are the coefficients for that. IRGB is a matrix component for RGB images or RGB spectrum. IHSI is the matrix component for hue, saturation, and intensity. So hue is basically uh, the, the color scheme or the color window of the image. Saturation is how much the color is represented, and the intensity is intensity is how significant that color is, and they are represented in that equation as they are. Uh, Regarding the model, we'll be using Rothermill's surface fire spread model. This is a link to the research paper, and this is available to view publicly. So Rothermill's surface fire spread model takes into consideration the heat conduction patterns, the wind patterns, the slope. And using this model, we'll be developing another model where we can predict the spread of the fire. So in the heat conduction model, we follow the concept of conservation of energy. So when we divide the area into cells, the forest area into cells, each cell can be in three states. So it is either on fire, it is not on fire, or it is already burnt out. So we can establish a few rules. So if a piece of land is burning, then it should eventually go out to the burnt out phase or the extinguished phase. And the next one is that if a cell is currently burning, it will eventually burn itself out in time t. And if a cell is not on fire and the surrounding cells are on fire, then at any time t, the next cell will be on fire. So this is basically the heat conduction model. And a topographical model. So the main factor in topographical model is the slope. So based on the slope, uh, it determines how fast the fire spreads. So a jagged terrain will definitely suppress the fire, than a downward slope. And this model can be represented by this equation. So the probability of the fire spreading in for a particular slope is is a component of the probability spreading with zero slope, and the probability of it spreading with full slope, that is 90 degrees. uh, and for various other angles, we can add a cos theta component to it, and this is how the model is represented. We do similar modeling for the effects of wind. So the fire usually propagates in the direction of the wind, and we'll be able to represent it with this equation. It also depends on vegetation density. If the forest is really dense, then the fire will definitely spread faster. And this is a linear equation, so the relationship is linear. So if the vegetation density is high, then the spread of the fire is also high. And this is actually the highlight of this model, of this research paper actually. So previous research papers did not take into consideration the vegetation density, whereas this one does. And I've linked the original research paper here. Uh, and finally, this is our equation for a cell ij. The probability of the spread of fire is an equation consisting of the probability of fire spreading for slope, wind, and vegetation density. So using this model, we'll be able to determine the spread fire pattern of how the fire spreads. And this is important because one of the aspects of fire suppression is detecting it early, and the next part is damage mitigation. And this model will enormously help mitigating the damage. It can prevent harm to society, wildlife, and our environment. And we can definitely improve this model further. We can implement machine learning once again to calculate the actual probability threshold based on previous data. So the probability threshold is, I mean, if the probability of a cell uh, which will catch on fire is PS, then if based on a certain threshold, we can determine if it will actually catch on fire or not. So that is the presentation. Thank you so much.